Good morning, good afternoon to all of the attendees that are joining us today for this webinar of the EAGE-EAG Technical Community on Geochemistry. Thank you for joining us today for this very special session with Dr. Linda Stalker from CSIRO. My name is Maria Paula Borges, Community Manager at EAGE, and we are pleased to welcome you all to this webinar. Geochemistry impacts in high quartz systems for injectivity risk management and the art of the negative result. To start this session, then we count on the participation of one of the committee members of the technical community on geochemistry, Alok Chalani. So Alok, welcome. Thank you very much for joining us today. We're going to start this session with the first introduction of our community.
Thanks, Maria. I'll quickly, within the next few slides, introduce this joint initiative between EAGE and EAGE. So these are two different societies, and through this technical community on geochemistry, we intend to deliver wide-ranging programs and community engagement. And this webinar is part of that ongoing effort. We have organized joint webinars between these two communities before, and we'll continue to do so along with several other activities, which we'll outline in the next slides. So next slide, please, Maria. So basically, we are a really diverse group of individuals, from students to industry professionals to academics, professors, scientists from across the globe. We have a very active LinkedIn group. What sort of brings us all together is our interest and passion in geochemistry and application across various fields. We were established in 2021, so that was the first call for these communities. I've been part of this community since then, and benefited immensely. We have done some great things together, and we'll continue to do so in future. We have a pretty good presence on LinkedIn, so probably Maria can circulate the link down later, but just look up us on EAG. You'll have access to the previous communication as well as the future coming one. So again, we are really two big communities in this space: the European Association of Geochemistry and EAGE. And essentially, we are a fairly diverse bunch: organic, inorganic geochemistry, trying to explore the link between industry, academia, fundamental and applied research, and related themes. Next slide, please. The current committee setup, of which I'm a member of, as you can see, is fairly far-reaching. We spread across different corners of the globe, and from time to time, we also circulate calls for new committee members. So just keep an eye on that via social media channels and LinkedIn in particular. Next slide, please. There are a wide range of community activities, the EAG annual conference being the top one, the webinars, and again, we have a dedicated page where you can look up related news, career advice, and vacancy in the geochemistry field. Next one, please. All right, so there's the big LinkedIn QR code, and I feel free to scan it at the later stage, or just simply search in LinkedIn, and we'll be and you'll be able to find us without any issues. Next slide, please. So in terms of upcoming workshop, we have geochemistry's role in advancing climate change and energy transition research. So that's up and coming, and we also have a dedicated session, and it's all part of the EAG annual workshop, EAG annual conference in Toulouse, upcoming in June. So if you can make your way up there, that'll be great, and you'll be able to meet a lot of committee members and participate in this very interactive and sort of well-designed workshops. On to the next one, Maria, please. And so upcoming, what we have the International Meeting on Organic Geochemistry. This is all for organic geochemists, and there is a call for poster that is ending on 3 August. And again, this shows that we are sort of fairly diverse, active across various subdisciplines, even within a narrow field of geochemistry. Next, I think that was the last one, Maria, or we got one more. Of course, carbon capture and storage, ending right on the theme for the talk today. So we have a call for abstracts. Just get into the EAGE.org and submit your abstract. I'm sure it'll be a great event. I think that's all for me. I'll hand you back, Linda, for our speaker introduction and the commencement of the webinar. Thank you.
Thank you, Alok, very much for this introduction. So that was a brief presentation of the hosting community of this nice webinar. So now we can move forward to the next point of our agenda, which is the presentation, Geochemistry Impacts in High Quartz Systems for Injectivity Risk Management and the Art of the Negative Result. Then our invited speaker today, Dr. Linda Stalker. She obtained a PhD at the University of Newcastle upon Tyne in 1994, focused on the rate of CO2 gas fields, following the award of her Applied Geology Honours degree at Strathclyde University. After postdoctoral research at the University of Oklahoma, she moved to Statoil in Norway. Linda joined CSIRO in 2000, working in research and management, ranging from research in hydrocarbon exploration and production to CCS research in monitoring and verification, geochemistry, social engagement, and outreach. Management roles have included Science Director for the National Geosequestration Laboratory, Group Leader in Exploration Geoscience, and Acting CEO of the Western Australian Energy Research Alliance, mixing research and strategic management. She is currently a Senior Principal Research Scientist at GSIRO and a State Leader for Western Australia. Dr. Stalker, welcome to this webinar. Thank you very much for preparing this presentation and for sharing it with the wider geochemistry community. Dr. Stalker, we can't hear you. We can see your screen, but we can't hear you. Check
Yes.
if I can't unmute you. We still can't hear you.
I had to double unmute.
Okay, no worries. Now we can hear you.
Right, here we go.
Perfectly.
Never gets any easier, does it? So thank you for the opportunity to present with your community today. And I'd just like to say that some of this work is definitely could be presented better by Ernie Perkins, who I see is on the call today. So I'm going to talk about how we use our geochemistry sort of modeling to try and help us understand one of the major risks that relates to doing carbon capture and storage, and how quite often the results are really quite dull. But first I'd like to begin by acknowledging the Whadjuk and Noongar people as the traditional owners of the lands that I'm speaking to you from today, and pay my respects to their elders past and present. So there's been quite a team that's been working together on sort of trying to look at geochemical impacts from CO2 injection in the subsurface. And I'd just like to acknowledge Mushtaba Saedi, who's now at the Global CCS Institute, Ewan Mai, Claudio Delapiani, Ryan Noble, and now Alok Chowdhury, who are all working at CSIRO on this topic. I thought it was probably worth mentioning briefly what CSIRO is. It's the Commonwealth Science and Industrial Research Organisation, which is a Commonwealth or federal government agency for research. It's one of the world's largest multidisciplinary science and technology organisations, with over 5,000 dedicated people working across 58 sites, most of them in Australia, but a few globally. And we are very fortunate that we get a lot of state-of-the-art national research infrastructure to play with as we go along. And they've measured that we've delivered 7.6 billion Australian to the benefit of the nation in the financial year for 2021. But we are a bit of a unicorn. There's not many sort of federal or national agencies quite like this. So I'd like to move on to sort of give a bit of an outline about what we're going to talk about and sort of try and illustrate some of the things and the takeaways that we want to pull together. So today I'm talking about carbon capture and storage, the storage part of carbon capture and storage, and how people are concerned about when you inject CO2 into the subsurface that we might have geochemical reactions. And when we've been doing this work, we have had a few of our colleagues going, why are you doing this again? So I will explain why we think we're doing this again, talk about some of the methods that we've been using, and then really sort of like hone into the work we've been doing using batch reaction modeling to see if this method or approach is actually sufficiently fit for purpose for decision making for large scale carbon capture and storage projects. So can these studies inform us to predict injectivity risks more broadly? And then towards the end, I'll mention the fact that it's not just CO2 we're putting in there, and can that become a challenge as well? So why are we doing this again? Well, this is an example of sort of the workflow for storage identification in the subsurface. We want to look at, first of all, capacity, storage capacity. Is there enough space for the CO2 volumes that we want to dispose of? Will it fit in the formation that we've identified? We also consider containment. Will it stay there? Can we keep the CO2 in place? So as well as looking at faulting and a lot of work that's based in sort of seismic methods, we're also looking at things like, do we have a sufficient amount of sealing rock, mudstone, or shale overlying the reservoir where we can put the CO2 so that it doesn't buoyantly migrate up and out of the storage container. And then the third piece of the pie here is injectivity. So the examples that I've got here have all been in relation to a project that was happening here in Western Australia called the Southwest Hub Project. And what you can see is some example there of the work we did for the Harvey 1 well and the Harvey 3 well, where when we did measurements of various measurements, including permeability, before we did CO2 saturated brine core flood into the rocks, and afterwards we saw that in one well we got a reduction in permeability, and the other one we got an enhancement in permeability. So how do we understand that, and can we predict it for other sites? CO2 does get around a bit, is naturally occurring. When I did work at Statoil, I was working on the Sleipner field for the exploration and production, and it had about 10% naturally occurring carbon dioxide in it. So one of the things that we were trying to understand was, where did it come from? And we've seen that over the years on the oil and gas industry do get surprises. They would rather avoid hitting high CO2 fields, but some of the fields these days can be quite high, particularly in the Southeast Asian region, where you can see the K5 field in Malaysia is like approximately 70% CO2. So this is one of the reasons why the oil and gas industry are, I guess, more comfortable than others with carbon capture and storage as a mechanism for disposing of CO2, because they've routinely had to extract it out of hydrocarbons and then look at capture methods and then move on to storage. So there's a lot of reasons why they're quite comfortable with it. And they're comfortable with it from the ancient history from the past. And I jokingly say ancient history. I've referenced a lot of these in my my PhD thesis. There was a lot of work done in the Gulf of Mexico looking at the opportunity to find secondary porosity caused by organic acids and CO2 generated from kerogen during organic maturation, and people were starting to identify sort of relationships between reservoir temperature, the amount of CO2, and the fact that they were seeing enhanced permeability or enhanced porosity. And we were also comparisons between the Gulf Coast and Norway. You can see there's this partial pressure temperature relationship up to a point for the CO2. And if you can see the examples by Smith and Ehrenberg, it's a fairly straight line initially for the Gulf Coast and Norway, and then you see these outliers coming off at where buffering no longer can happen because the amount of CO2 present it gets a little high for it to cope with. So we've got all of these sort of light background pieces of information that CO2 and reservoirs, both clastic and carbonate, can have have an influence on one another. One of the other reasons why there is lots of really good information, particularly in the US, about the interaction between CO2 and reservoirs is because of the large amounts of enhanced oil recovery that takes place there. And this is a paper from 1984, where they did some experiments doing trying to mimic the water alternating gas enhanced oil recovery process, and they did note that the experiments indicate that any increased permeability expected with the dissolution of any carbonate cements is offset by the migration of clays that were adhering to the carbonate, resulting in no net change in permeability with the injection of CO2. So for all of the activities and changes that might happen because of geochemical interaction, they can have physical impacts as well, such as clays and fines migration that you can see as well. The results that they have posted in their table as well show that you can see quite a lot of changes in iron and carbonate concentrations as they go forward as well. And here's an example of when we see dissolution and core flooding with CO2 saturated brines. You can see that we start to lose a lot of fines and a lot of materials. We get enhanced porosity, but the concern is where did all that stuff go as well? And then to quote Stefan Baciu, Ernie and others, one of the things that you're trying to really unpack, trying to understand the geochemistry when you do inject CO2 into reservoirs, is that the chemistry of the formation water, the rock mineralogy, may increase or decrease the potential for CO2 capture through these reactions. And so there's been work done over the years looking at the brines present in sedimentary basins and how what the total dissolved solid impact might be on those formation fluids, and can impact those geochemical reactions reasonably significantly. So injection of CO2 into basic siliciclastic formations leads to mineral trapping of CO2 through precipitation of carbonate minerals. So what you really want to see is aquifers with brackish or low salinity waters, basic calcium and magnesium silicate mineralogy should be preferred for CO2 disposal because you're not going to have those issues. So what's changed? Not much. So to the present, so what we're finding is that now we're seeing that the regulator is now imposing some activities that proponents who may want to define an area for CO2 storage has to do a bit of geochem work here, and particularly some modelling. So this is an extract from the US Environmental Protection Agency Class 6 wells for underground injection. And it says here that you might want to use suitable programs such as Freak or potentially Geochemist Workbench. And they are advocating that modelling allows consideration prior to injection of the types of reaction like loss of carbonate, precipitation of carbonate, long-term dissolution of silicates that can change permeability, release undesirable elements, so heavy metals and such like, alter injectivity, and affect ultimate storage capacity. So if we see that the injectivity is getting low, we may need to drill more wells, so the cost for the overall project becomes more challenging. And the US is not alone in asking for work to be done on geochemistry for carbon storage locations. So this is an extract from the Australian Declaration of Storage that a proponent would have to submit. And in addition to all the other bullet points that are on this table, you are being asked to describe the geology of the storage formation as a minimum reactivity of rock types with the proposed greenhouse gas storage substance in both the reservoir and seal rocks. And also a bit of a nod to the fact that you want to understand the reservoir fluid parameters, including chemical composition, pressure and temperature. So whether people decide that this is cutting edge research and development or not, we've now got 2 jurisdictions saying you will provide this information and you will have done it appropriately. So what are the methods that are available for actually trying to address these demands from the regulator? Obviously, we've got laboratory processes, we've got field studies, and also modelling. So what we've got here is a schematic of a batch reaction system that the University of Queensland, Julie Pearce, has developed over the years and can put samples in and take dip samples and actually measure the actual interaction between the CO2 saturated brine and the sample holder and the minerals that are being used. And you might want to take note to the fact that it's not only is there CO2 in some of these samples, but they are adding contaminants as well, and we'll have more on that later. So other types of laboratory experiments include doing X-ray CT with X-ray transparent core holders and actually flooding CO2 saturated brine through those cores. So you can see sort of like physical changes in saturation, but you can also take fluid samples as this moves through. So that's another method, and as you can imagine, once you get into the laboratory and you start playing with like medical CT scanners and large-scale core, the price or the cost and the time to pull together these sorts of pieces of work, and that's just for sort of one sample, starts to become quite challenging. But even more expensive is going to field work, and this is the CO2 CRC Otway project. I think it's now called the Otway International Test Centre. We were working there with the CO2 CRC many years ago, collecting fluid samples from the subsurface where there was an injection test. So the Otway Stage 1 test, there was an injection of mostly CO2 into the CRC1 well, and monitoring in the bottom of the Naylor 1 well. At the same time, there was an extensive monitoring and verification program looking at air monitoring, soil gas monitoring, groundwater monitoring, seismic monitoring. But this was actually looking at the evolution of the fluids as they migrated up dip into a depleted gas field. And you can see on the right, there's a sort of schematic of the geology in the area of interest and a kind of like a cartoon of what the components that were in the well and what actual fluids we were able to sample. And so these funny little U-shaped tubes with a little ball valve on the end. We had one in the gas cap, we had one just on the gas water contact, and we'd one deep in the water. And we could take regular fluid samples at reservoir conditions up into that little yellow sea container you see on the left hand side and actually sort of measure fluid compositions quite systematically. The site is still ongoing, there's still research happening, and they're actually working what they're going to do for the stage 5 development and research for CCS and even hydrogen storage at the moment. So this is some of the equipment to build and do the fluid sampling. So we've got all of these lines going into the wellhead, going through a very complicated packer to sort of seal off from the other levels, and a whole lot of gases lifting the fluids in and out, and what looks like a quite tired Chris Borum sitting on a chair there. So there was a lot of, I think the best thing I could describe it as is tap juggling to try and get these fluid samples out. And working with the team, we were able to sort of identify when we were getting first breakthrough of the CO2 from the injection well to the monitoring well, and we'd added a whole bunch of chemical tracers, but actually the most effective thing that showed the change in the arrival of the CO2 was actually the carbon isotopes in this case. So we had a lot of interesting time just trying to work out how many months it would take for 300 meters of transit of those gas fluids within an actual porous media. Suffice to say, it's not a cheap pastime, but we got a huge amount of benefit in data, even though while collecting the samples was really effective, actually trying to degas and actually get the information out of really high pressure samples was actually really quite challenging. So one of the things that I was going to also draw attention to is when we're doing carbon capture and storage, when we're doing these models to try and understand and de-risk potential sites, we've got two sort of different sites that we're going to be looking at. One is depleted gas fields, just like that Otway example, and the other is what is termed in the trade as saline aquifers. And this image from CO2 CRC doesn't actually necessarily give the true extent of what a saline aquifer could be, because it could be like much bigger than a depleted field. A depleted field might have lots and lots of wells and lots of data because they've drilled lots of wells, taken lots of core samples, they've got lots of pressure data and other information where you can do sort of good history matching. The saline aquifers, you're much more constrained on the amount of data and equipment and core samples and so forth that you might have, and it could be over quite a vast distance and depth range. So it's much harder to try and like work out what the input parameters are for your model in a saline aquifer example. Nonetheless, we've given it a red hot go in trying to sort of work through that. And so we've developed over the last 4 or 5 years a sort of batch reaction model methodology for computer modeling. And so there's two parts to what we've been doing. One is like gathering the data that we need for the input, and then is the protocol we use for actually doing the geochemical modeling. So first up is like, does the data already exist? And if not, we have to get out there and get sampling, cleaning the samples. We need QXRD data if we don't already have it, filling those gaps. We might also get additional information like mercury injection porosimetry, and we do need porosity data as well. And then once we've got all of that and some like background information on the operational processes, so what pressure and depth are you going to inject at? What is the temperature of the interval that you're going to go into? And so forth. How long are you going to inject for? At what rate? We can actually then crack open Geochemist Workbench or whatever software package that you're going to use, and actually start to sort of build some models. And when we do that, we first of all we actually sit down and we working collaboratively with the geologists to try and work out what base case is. So what is a really sort of solid example of what your reservoir interval is and what your top seal interval is. And there may be more than one facies, so you may need to actually do several base case models. It will really depend on each of your sites and situations. And so that base case will get built. And then once we've sort of established that, we'll look at the data and try and find out if there's certain mineral species that are maybe more highly represented than some of the other samples. So we really do want to see the best and the worst of the reservoir and the top seal so that we can get these end members. And it's really quite challenging sometimes to get people to sample appropriately, because if you're from an oil and gas background, you want to just sample all the really high porosity and permeability samples that are really clean, but that doesn't give us these sort of outliers or end members that we want to try and look at. So with the sensitivity cases, we're maybe changing mineralogy, we might change porosity to increase the amount of fluid present to increase the reactivity, or change surface areas and so forth as we go along. We might, and we quite often will include a stretch case where we're trying to slightly break the model, but not really, and we're not trying to sort of go out with the bounds of the data that we have actually collected. It's really tempting, and this is why the negative result is actually to be kept close is you don't want to see any reactions. This is the nub of the whole thing. It's like a negative result is a good result for CCS. If you're not making any changes, you're not dissolving anything outrageous, you're not precipitating anything outrageous, and it's all pretty much as you had it, that is a win for your risk reduction. And so if that's all happened, you review your outcomes, you're going to fill out your declaration of storage or whatever relevant submission you need to do. And if once you've actually started injecting and it doesn't necessarily match, you can still be pretty smug that you've got relevant data on hand if things don't quite go according to plan. And so then you may have to go to plan B, which may be core flooding or reactive transport modelling or some other methodology, which will take a lot more time, effort, cost, and so forth. But at least you've done this screening and it's given you like an indication of whether you've actually got a problem. So when you do those base case definitions, you are going to work pretty hard with the geologists. They've got valuable insights on the range of parameters, the depths, the mineralogy, the heterogeneity, and they may have additional insights depending on whether it's a depleted field or if it's a saline aquifer. So you're going to build that case, you're going to look at your top sealed data, your QXRD and your porosity, the duration of injection, as I said before, partial pressure CO2, formation fluid chemistry from the samples. If you've got fluid samples that have come from wells, they are frequently contaminated and can be very difficult to actually converge in your models. So we will also do some equilibration modeling to try and make sure that we get a reasonable representation without there being too much trying to sort of like manage models. So here's an example of a base case definition. It's a pretty clean quartz sample, a little bit of kaolinite, muscovite, illite, moderate porosity, bit high temperature, and this project was intending to do about 10 years of injection, and you can see that actual porosity, and I've not shown the permeability data here, but the change over a 10-year period is distinctly lacking, because if you start to actually look at the porosity measurements there, that's down to 6 decimal places to get any sort of like tilt on that line at all. Obviously, what we've been doing is calculating this by assessing the mineral volumes and density changes modelled, trading off the porosity. And the base case here shows that there's marginal evidence of porosity increase. So in a reservoir, if we've seen increasing porosity in the near term, that's not a bad thing. It's allowing us to continue to inject. We're not having to worry about things gumming up and the need for additional wells being drilled. And you can do a sort of like conversion, a calculation to get to permeability. So sad were we with it. We had such little change actually happening initially when we first started doing this. We actually started to muck about and actually try and present the data as a percentage of increase in porosity. So we get down to 4 decimal places to try and do that. But really, this is where we have to start to embrace the negative result. It's a good thing that we're not actually causing short-term negative changes and blocking things up. Then we've gone on to a whole heap of sensitivity changes where we'll change each of the minerals or key minerals that we've identified, and done things like, so you can see this example here where with base case 2, 5 and 6 we've changed changed mineralogy, and we've seen some slight permeability and porosity changes, and we've seen a bit of increased illite precipitation. We've got some other examples here where we've also had some changes because we've changed another mineral, but really we're still not seeing a whole lot of change. You know, we're still reporting it as percentage of increase in porosity rather than this absolute increase in porosity. So again, very, very minor changes. Even the stretch cases, we're starting to sort of actually combine different sensitivities. So, you know, we're increasing we're having a temperature drop because the CO2 is cold coming into a hot reservoir. We've gone for a high surface area option on the minerals, and we're you know, we're still really struggling to actually get much of a change, and still reporting as percentage of increase in porosity. And this final example here, where we've messed about with porosity, we've added different amounts of pore volume flushing through as well to really try and make any changes. We've done the same thing with top seal. It's a little harder sometimes because the porosity can be quite low. And you can see that we've again just really struggled to make any great changes in porosity or permeability in the top seal. Of course, in this case, we want to actually precipitate more minerals rather than dissolve any of the top seal. We want the top seal to stay competent and not have anything happen. And even when we're starting to report to 5 decimal places, really not a lot happening there again. So working through all of that, we get a whole lot of negative results. Like so, nothing to see here. Pretty much. So again, present as percentage of porosity change. It's hard to do to show too much change. We resorted to these sort of bar charts that we had to try and actually show where any slight evidence of change would happen. Now we've done these sorts of studies quite a few times now, and more often than not, changing the surface area of any of the minerals is the one thing that will make the biggest change. And because we know that the surface area numbers can be a bit uncertain, if everything else is not really making much of a difference, which you can see in the top seal particularly, and in the reservoir to some degree, we are not really seeing a whole lot happening. So to conclude that, the messaging around and the methodology that we've used, we've seen fluid rock reactions in that particular example had a very small increase in reservoir porosity and permeability. And we really had to do quite a few things to the reservoir before we actually started to see any reduction in porosity at all. In terms of the top seal, we could only really make anything change if we had a really strong temperature drop near it, or whether we've dialed up the initial top seal porosity, but it was still only 0.2% of the original porosity actually changed. But here's the thing, it's not just CO2 we're actually putting in there anymore. Now people are starting to realise that there are additional contaminants that may come in with the CO2. For example, from solvents or sorbents, so amines may actually be introduced. Depending on your capture method or your original source, you may have some crossover. During transportation and compression, some things might be concentrated, some things might drop out, and there may be changes during utilization, and so forth. So we've actually got to start mapping any of these contaminants. So what we have seen over the last few years is an increase in the variety of sources of CO2 that might be used for injection. So this is a schematic from the Global CCS Institute's annual status report from 2020, and you can see I've sort of like highlighted the natural gas processing row there because it's the earliest pieces of work, and it's the largest amounts of CO2 relative to any of the other activities. And you see from 2020, we're starting to see all those blue circles, which are future projects or projects now in play. They're all starting to be in other areas like cement, steel. There's some possible waste to energy and so forth. So it's always been an easy one to actually sort of start on thinking about natural gas processing. But now here's the 2024 report where you can see that aluminium, waste to energy is increasing, power and heat generation, pulp and paper, iron, steel, cement, chemicals, all sorts of different things, which all have different amounts of contaminants potentially in the CO2 entrained in the gas. So at the moment, each emitter has potentially different starting materials and conditions with potentially different co-contaminants. And in the near term, we're trying to define what these contaminants are, what the risks of them are in the CO2 stream for the reservoir and for other reporting obligations. So, oh wait, let's go back to the Australian Declaration of Storage again, because in here it actually says that we actually have to look at the reactivity of rock types with a proposed greenhouse gas storage substance. So now we're actually having to go back round again and look at some of the work that we've done and actually consider the fact that we've only done it up till now in pure CO2, and we now have to start adding other potential contaminants, and what does that do to our models? So how do we know what contaminants to add? Well, we've been working on a separate piece of work with the Australian government, trying to define what they call the National Action List. And this is like a list of all those potential contaminants that could cause environmental or human health impacts if they are actually released. But the sidebar issue is the conversation around, well, what might it do to the geology as well? So this is a couple of screenshots out of the actual report. This is the interim version. We're actually working on the full version, and we're starting to publish information on how we arrived at these numbers so that we can get them peer reviewed. So we've got things like, not actually shown on here, is like oxygen is a contaminant. Oxygen is not going to be an environmental or human health impact, but it's certainly going to have impact on the mineral chemistry going forward. So now we're having to sort of like work through this and go, well, okay, NOx and SOx may definitely appear in some of the gases that we're, the CO2 rich gases that we're looking to see proponents store offshore and onshore as well. So we're starting to sort of work through all of this and see what impact that has on all sorts of the aspects of the modelling of the chemistry going forward. So we're going to have to rinse and repeat a whole bunch of work and start to really sort of test some of these different compounds and see how they impact going forward. So I'm really kind of at the end of sort of talking about what we've been doing and why geochemistry is actually important to CCS for injectivity. And what we have managed to do is build up a portfolio of studies to try and tease out what are potentially the cut-offs before challenges start to manifest. So we, nothing changes in the sense of like it's much easier if it's lower salinity, not too hot, simple mineralogies. Once you start to deviate from some of those particular cases, then you start to get, potential for changes that you don't necessarily want. Geochemical interactions still cause fines and formation damage, that's not changed either. But we do want to encourage being very pragmatic about when you do your modelling and embrace those negative results when you don't really see a whole lot happening. We're really excited about trying to get some more core flooding done with some geochemistry, core flood effluent, and using a lot of this information to actually go back in and validate some of the reactive transport modelling and calibrate the basic geochem studies that we have been doing. So with that, I'd like to thank you for your attention and open for questions.
Thank you very much, Dr. Stalker, for your presentation today. It's very fruitful and enriching. We do have some questions from the audience. Then let me extend them to you so that we can, of course, discuss this with our attendees. So the first question that we have is, any information regarding the thermodynamic database used in the geochemical modeling?
I think Alok might answer that question for me because he's my GWB wrangler. So I'm just going to pass that one on.
That's good. Yeah. So for any kind of like geochemical modeling, not exclusive to carbon capture storage, but any kind of geochemical process that you want to model, whether it's supergene enrichment, acid mine drainage, or anything else, the two key information thermodynamically wise you need is the data for the formation or dissociation of any reaction that may happen in your system, assuming you're using frequency, GWB, kind of software which uses the law of mass action to calculate log K. And the source of data in this software actually goes back to a software called Supercrit 92. And that was basically Helgeson, Eric Olker, and a bunch of other people, they developed that essentially sort of like a mother database of all these thermodynamic parameter that works quite well. In different software, they have sort of like expanded on that. But that one citation is really the key for all thermodynamic properties. So that helps you to calculate the log K of your different reaction that's happening in your system. That's how this software is calculating equilibrium for. The other set of data you need is kinetic data. For example, what are the dissolution rates of calcite, quartz, pyrite, things like that. That basically comes for all experiments. So people have experimentally measured dissociation of these minerals. So it's a matter of like finding the right reference, going through the experimental bit and seeing whether those dissolution rate constants are fit for the purpose of whatever modeling you're doing. So it's all out in the public domain. Many softwares, they come with this inbuilt thermodynamic databases, and it's sort of like it's all like public access. Yep. Next one.
Thank you very much, Alex, for your
Good answer, Alok.
Okay, now we have another one. It says, are you using an autoclave cell to investigate in CO2 rock interaction tests? If so, what is the operational conditions of your rig?
So currently we are not. We've got different rigs for different purposes, and we have a lot of pretty full-on rigs for geomechanics here rather than the geochemistry. And the example of the schematic example I showed was in a paper by Julie Pierce and the team at the University of Queensland. So I suggest have a look at their work. Our team are talking about doing it, and I used an autoclave. I used power reactors in my PhD. I just don't want to go back there again. It's actually it's challenging to get the right materials because CO2 is not the friend of stainless steel, and so you may have to use Hastelloy or super duplex and really sort of try and do a lot of really careful development. Even the seals that you might be using, you can't use conventional seals because the CO2 gets into the seals and deforms the seals. And then you've got to make sure you've got proper liners in there, otherwise you're just going to cause reactions because you're dissolving your system. So it can be quite challenging. We did do some similar work for core flood using the whole core flood equipment as basically a dynamic sort of autoclave pushing CO2 saturated brine through. We collected the core flood effluent, we measured it, and we realized that we could see the dissolution of the steel inside the core holder as well as the actual other things that were going on, which kind of upset Ali Saidi as we were watching his machine dissolve gently in front of him. So it's not for the faint-hearted, and there's a lot of information out there. Go talk to people if you are even thinking about building a cell, because they are, high pressure rigs are quite challenging, especially with respect to health and safety, as well as actually just not having massive artifacts.
Thank you, Dr. Stalker. Then we have some more questions. Mark asks, what tracers are used and what info is derived from them?
So that's a really good question. People have been either using naturally occurring tracers. So if you're interested in looking into that, there's Stuart Gilfillan from Edinburgh University has published a lot of papers where he's measured things like noble gases and other tracers to try and understand the sort of behavior and the migration and the movement, partitioning and so forth in the fluids as they move. We did add chemical tracers at Otway in a couple of different cases. One was to sort of like try and use it actually for monitoring and verification purposes. So we wanted to put things in that you wouldn't naturally find in groundwater or soil gas or the atmosphere, but it also gave us an idea about sort of like rates of movement and potential saturation. And we've done some other work there using ester-based tracers, trying to use that to work out CO2 saturation in situ as well, using push-pull testing. So there's a few papers around that I can direct you to on that if you need them.
Thank you, Dr. Stalker. Well, I think we can have space for 3 more questions very quick. So I have here, have you tried applying machine learning in determining the top seal?
No, not so far. But I think once we've got a few more pieces of information together, I think that's one of the things I think we'd like to try next, is to see if we can take the data that we have generated and see if we can sort of work out boundaries and parameters so that we can then in the future go, yeah, this is going to be a really low risk example and here's the reasons why. So that's what we'd like to do, I think.
Perfect. Then we have another question from Anthony. An interesting comment you made. Along the lines of changing the surface area of the minerals is what causes a change. How do you see the CO2 storage in basaltic rocks, where porosity is to a large extent due to secondary porosity of fractures? Would this have an ideal amount of surface area for CO2 capture?
So there's a lot of work going on in the CarbFix project in Iceland that some of you will be familiar with. And I think I am not so familiar with this particular area, but what's interesting is that those basaltic rocks are like brand new, fresh, lots of unweathered surfaces. They may be sort of fractured. You're putting in cooler waters, and you could be causing lots of like instantaneous fracturing. All sorts of things could be going on. And that means that the potential for reactivity is greater than an old cold basalt that you might find, say, on continental Australia. So I don't think all basalts are equal in terms of like how they might behave, and it will be weathering less versus less weathered, and really understanding whether there's connectivity and reactivity. So if you don't have good sandstone reservoirs, that might be what choices you might have for localized CO2 disposal. So there's a lot of people working in that area trying to understand that as well. CSIRO included has a program of work called Carbon Lock, and so they've got teams of people trying to sort of understand that a little bit more in detail.
Thank you, Dr. Stalker. Now, for the sake of time, then we will have 2 more questions. What was the phase of CO2 injected? Was it dry and supercritical CO2? If so, have you monitored halite precipitation,
yeah.
halite precipitation along the core flow experiments?
That work I haven't really gone into in any detail, and I don't think we've got that published. I think that's a lot of work that Ben Clennell and other people have done. So I really, they've done CO2 saturated brines. Like they actually will do different. Sometimes they will start with water, CO2, a synthetic brine that represents what they think was the original brine in contact with the rock. They then may saturate with CO2. They may flush it with CO2, supercritical CO2, and then they may flush it again. So they will do cycles of different things as they go through. So it depends, unfortunately, is the answer to that question of what sort of experiment they're doing. So sorry about that. I can't be any more specific.
Thank you, Dr. Stalker. Then the last one by Jose. Have you tested this technology in West Africa, such as Angola, Nigeria?
So I'm not quite sure which technology you mean. If you're meaning CCS, there has been, gosh, quite a few years ago now, there was it wasn't even an experiment. It was an attempt at a commercial scale project it's called In Salah, and it was in Algeria. And there was, I think it was Statoil and BP were actually disposing of some of their CO2 further down into a gas field that they were actually extracting the hydrocarbons from. And in the end, the monitoring and verification data indicated that they were getting uplift and early breakthrough, which was interpreted as actually activating a critically oriented fault, and it was actually starting to cause a bit of shear. So because you have a good monitoring network, and they were actually using INSAR data, satellite data, to see ground heave, they identified a couple of issues with 2 or 3 different pieces of data, and they decided they were not going to inject the CO2 anymore and just keep producing. And when they stopped injecting the CO2, the pressure dissipated and there was no actual leakage or anything like that. So it's actually been a great test case subsequently of people actually developing tools for monitoring, understanding ground heave, tilt meters, all sorts of different things to be used in monitoring. And you can use that data set to go, well, would my new gadget actually be able to determine that that was actually happening? Yes, it would, or no, it wouldn't, based on the historic data from that particular project.
Perfect. Well, those were the questions from our audience. Thank you very much, Dr. Stalker, for joining us today, for giving us, for sharing with us your experience, your knowledge this time, for all of our community to update also their knowledge on geochemistry impacts in high quartz systems for injectivity risk management and the art of the negative result. Thank you for joining us today.
Thank you very much for having me.
Thank you also to all of our attendees for joining this session today. We hope it was fruitful and enriching for all of you. And of course, we would like to count on your participation in our upcoming activities. As Alok kindly mentioned at the beginning of the session, our dedicated sessions and workshops at the EAGE Annual, our participation at EMOG, most likely in the next few months, also with a new edition of our webinar series. So we hope to count, of course, in your participation in all of our activities. Thank you very much for joining us today, and I hope to see you all again soon. Have a good day.
Thank you.
Thank you. Good to see you all.
Thank you.
Thank you.
Thank you, Mariad.
Bye-bye.
Bye. Thank you, Dr. Stalker.
Thank you very much. See you later. Bye.
Later. Bye-bye.